Okay. Oh, and let me bring you all back to life on my monitor. There. More people are here. Hi, Megan and Anna. So we've got two volcanoes up in the top middle, and then this Dairy Queen. Does anybody know what that cone is called? Have you ever seen a cone like that? We don't have Dairy Queens around here, but we had Dairy Queens where I grew up. Anybody ever had one of these? Anna, you have? It's a dip cone. And if you were to take a bite of this dip cone, you would encounter this crunchy chocolate outer coating, and then there would just be vanilla on the inside. And I think they just do this. Oh, I went through all that trouble to get my picture here, and then my picture is not even here. So they just do this swirly thing, and then somehow they dip the whole cone in a bunch of liquid, and it hardens on the top. So the question, number one, is how are the items on the right similar, and how are they different? And in the bottom picture, oh, that's the one I'm covering up. We'll get to that one in a second. So does anybody see any similarities or differences between the volcanoes and the dip cone? Megan, do you? You're the only one with your mic off. It's okay. How about Jace? Do you see any similarities or differences between this dip cone and these volcanoes? How about you, Anna? Anything similar or different? I can think of a lot of things. I mean, they're kind of similar. And they're
like it's hard on the outside and like soft on the inside.
exactly. So I'm going to zoom in here, and this diagram over on the left, it shows steam and ash coming out the top, and then there's a crater and the flow, and then it says alternating layers of lava and pyroclastic material. So there are two kinds of material that hopefully you've been studying, mafic and felsic stuff. And they're using different words for this, but the one that melts and actually flows is the mafic stuff. That's what they're calling lava in this diagram. And the pyroclastic material, that's the felsic stuff. That's the stuff that's so gooey that it doesn't really flow, it just builds up pressure. So this has alternating layers. And this dip cone over here, it doesn't really have alternating layers. It's got two layers. It's got the sturdy stuff on the inside, and then it's got this chocolate on the outside. And the thing that I think is, to me, that's really similar is if you didn't have the ice cream there, and you just poured some chocolate sauce on top of this cone, would it pile up and make a steep volcano shape? You can nod or you can shake, or what do you think? If I just had some chocolate sauce, like it's covering this cone here, by itself, can it make a volcano? Can it form a big, tall, steep tower? Yes or no? Yes? No? No. Okay. No, it can't. But with the ice cream below, it can. So that's like this volcano over here. The lava itself is never going to make a steep volcano like these ones in the picture. These are both called composite cone volcanoes, and they're pretty steep just for compared to most volcanoes. And there are other kinds of volcanoes that have just lava, and they never get to be steep. So the reason these are steep is because they've got the light-colored stuff in between, and that gives them the structure. That can pile up. And when they explode, they can either erupt, and they have a gentle eruption where more chocolate sauce pours over the top and then hardens, and that's these dark layers that you see in the diagram, or they can have a really explosive eruption where it looks like the center picture, and a bunch of ash goes up, and that settles down. When the ash falls, that builds it up higher and steeper. When the lava comes out, that just coats the outside. So in this dip cone over here, the ice cream is like the ash because it actually has structure, and the chocolate sauce is like the lava. Now it's not a really good example because if you melted the ice cream cone, the ice cream would melt, the chocolate sauce would melt, it would all melt, and it would run away. But in the case of these volcanoes, the light stuff, that doesn't really melt and run away because it's not runny, it's viscous. So the point of showing you that is to show you that first, there's some volcanoes made up of multiple kinds of lava and material, and second, that the stuff that's in there that makes it steep, that's the felsic stuff. Hopefully you studied the Quizlet, so if I say felsic, you know what I'm talking about. All right. Now, the second question, in the bottom picture, what makes I don't even know, hey, good morning. I don't even know what this word is. It looked kind of like diapers, but we could look it up. I'm sure it's a real earth science term. I'm just not familiar with it. But what they're calling the diapers, see right down here where it says rising diapers? I'm sure I'm saying that wrong. That stuff that's rising, I would just call that molten plate. This plate right here is going down and it's melting. And when it melts, it's rising up. And it's just floating up to the top, and they're calling it diapers for whatever reason. My question is, what makes that stuff rise? So why does it rise? So there's a simple answer to this that everybody should know. You should be able to tell me, the minute you hear rising and I ask you why, you should have an answer. But the second part is more complicated. I'll ask you why again. So does anybody know the answer to the first why? Tommy, since you just got here, what makes things rise? Density. So are these diapers dense or not dense?
Not dense.
They're less dense. So they're less dense than the stuff around them, and that's what makes them rise. Now the harder question is why? Why would they be less dense? They're made of, if I zoom in here, they're made of melting, can't really see me anymore, but they're made of melting ocean crust. And does that give anybody any hints? So this is the ocean crust. It goes down in here, it dives, starts to get hot, and then it melts. Why would it be less dense when it melts than the stuff around it? Any ideas? I don't expect you to know, I'm just curious before I tell you the answer, before I tell you what I think is the answer. Okay, so here it is. I'll tell you the most important part first. That sediment, can you see the sediment in this picture? Okay, the sediment isn't the color I've been drawing it. I've been drawing the sediment felsic. Felsic means it's light in color. The sediment here is what color, Soli? What? It's not black. Reagan, what color is the sediment in the picture? If you don't know, just unmute to say you don't know.
I don't know.
Don't know? Elijah, what color is the sediment in this picture? Just seeing if you all know what I mean by sediment.
I think it's like reddish black.
I think it's a little different than that. Anna, do you know? Maybe the color you're seeing on my screen is different.
Is it the like blue gray kind of stuff?
Yeah, now for me it looks purple. It's right in here. This stuff, yeah, I guess on this screen it looks blue-gray, and on my screen it's definitely purple. Who knows by the time it gets through the internet to your house, but it's this stuff right here. And if I were to draw it, I would make it the same color as this, because that's a nice light gray, and that would be a good color for it. But anyway, it's this purple stuff. And for whatever reason, they've drawn the ocean crust down below. They made it darker, that's good, but this is the kind of reddish stuff there. So as this goes down and sinks, we've got two things that are melting. One is the ocean crust, which is mafic, and the other is the sediment on top, and the sediment is felsic, and that sediment has water in it. So when you heat up water, if it goes down into the earth and gets really, really hot, what does water turn into? It turns into a gas. So it releases all these bubbles. So it's like the film canister submarines, except it's just boiling. So there are two reasons this stuff rises. One is it's got a lot of sediment in it, And the sediment is made of felsic stuff, which is less dense, so it rises. But also it has a lot of water in it because there's water trapped in this mud. And when the water boils, that creates bubbles and makes all this rise. So when this stuff rises, it's got two kinds of lava in it. It's got the ocean crust kind, and it's also got the sediment kind, plus it's got water, which can build up pressure. So these volcanoes can either ooze out when the dark stuff comes out, or they can explode because they've got the gooey felsic stuff from the sediment. And they've also got steam in them, and the steam builds up pressure and makes them explode. So the answer to that question, why do the diapers rise, or whatever those things are called, it's because, well, I can give you 3 reasons. When you heat things up, they become less dense, so they just got heated up. They're also made of some felsic material, which is less dense, and they also have water in them, which is going to turn to steam, which is less dense. So the fact that there's steam in it, there's felsic stuff in it, and it's getting really hot, all those things make it rise. And it just burns its way up through here until it comes out. Okay, next thing on the agenda. I've got to zoom way out here. Plate boundaries, Google Slides, that's just something I can refer to. The rock types Quizlet. I'm going to quiz a few of you, see how you're doing on this. Go to my flashcards. So the answer to this, each one is going to be either, mafic or felsic. So that the answer to each of these questions is either mafic or felsic, and I'm going to be choosing people. Once I get my popsicle sticks program here. I'm in physics right now. Okay. Skylar. No Skylars there. That's shame on Skylar.
RJ.
RJ. Less dense. Mafic or felsic?
Felsic.
Felsic. Very good.
Mandy.
Mandy. No Mandy.
Megan.
Megan. Darker in color. Mafic, yes. Okay, next one. Found in the mantle.
Tommy.
Tommy. Found in the mantle. Found down deep, that's a hint. Is it mafic or felsic? Mafic. The mafic stuff is dense, so it's going to be deep in the mantle. Found in continental crust.
Harriet.
Harriet. Felsic, yeah, the felsic stuff's less dense, and the continental crust is on top. Found in ocean crust.
Laura.
Laura, no Laura.
Cassidy.
Cassidy, no
Elijah.
Cassidy. Elijah.
Mafic.
Mafic, yes. Ocean crust is ocean crust because it's made of dense stuff and it sinks down low and gets covered with water. So that's why ocean crust is mafic. The more dense kind?
Reagan.
Reagan. Which one's more dense? Come on, Reagan. Either mafic, felsic, or I don't know. Mafic, yes, or not even or whatever. Okay, gets its name. This one I'm never going to ask you on a test or a quiz unless it's a bonus. Gets its name from having a lot of feldspar and silica. Although I think you could probably figure this out.
Melissa. Tyler.
Tyler, no Tyler.
RJ.
RJ again. Feldspar and silica. What does that remind you of? Mafic or felsic? Felsic, yeah. The fel comes from feldspar and the sick part comes from silica, so felsic. Gets its name from, I'm going to tell you this because it's the other one. Having a lot of magnesium and iron, that's mafic. The Ma is from magnesium and iron, the symbol is Fe. Less viscous. So this one's the runnier one when it's molten. Soli. Mafic or felsic? 50-50, yes. Mafic. Mafic is the runny kind. All right, more viscous. Well, that's going to be felsic. I'll just tell you that. Lighter in color, Jace. 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 See, this is why I need Jace's camera on. I think Jace is gone. Jace? What's that?
I'm not gone.
Okay, it's lighter in color. Is that Mafic or Felsic?
Everyone's called, but like, the one
It's either Mafic or Felsic.
I don't know which one's called anymore.
Okay, well, this is Felsic. Felsic's the one that's lighter in color. The seafloor sediment. Megan, which one's in the seafloor sediment? The stuff at the bottom of the ocean. Oh, no guess? 50-50? Who knows? Raise your hand if you're certain. Anybody? All right, Harry. What's that, Megan? Felsic, yes. It comes from the continents and it washes onto the ocean floor. So it comes from the continents, which are high up and less dense. Eruptions are more gentle. So this is the one that gives the gentle kind of eruptions. Harriet. Mafic, yes, because it's runny and it doesn't build up pressure. Eruptions are more explosive, that's Felsic. That's the other one. Makes steeper volcanoes. Anna, which one makes steeper volcanoes, Mafic or Felsic? Felsic, because it's gooey when it has structure and piles up. The runny stuff just goes and it doesn't pile up. And produces less steep volcanoes, that would be the Mafic. And then we're done. Okay, so on Google Classroom, I assigned that again. So if you feel like you've got all those and you don't need to study that again, and you're set for your quiz, you can just mark it done. But some of you definitely need to study it again. Although if you guess, you should get 50% on this quiz. Just guessing, you should get half of them.
I did that once with the section of, of the quiz, and I got every single one wrong.
Yeah,
6 questions.
that would happen to me too. Shouldn't. I mean, you beat the odds. So, more plate boundary drawing practice. Use this drawing template if you want. I was just telling people who showed up early, I'm going to give people in here, or I gave people in here this sheet. I'm going to use this sheet. If anybody wants this sheet, you can either print it out from my website, or you can go to Google Classroom and print it out. But it's just got a little checklist that I want to fill in as we're doing these, and I'll explain why as we go. So let me switch to this camera, which I'll probably have to turn off and turn back on. Yeah. I don't know why. Hopefully it'll work. There we go. So this is what my sheet looks like. Oh, now my mic isn't working. Testing, testing. Can you all hear me now? Okay, it told me my mic wasn't working. I just realized I'm going to get my note sheet out just so I can show you where we are. But we're going to be drawing plate boundaries just like we did last time. And in fact, I'm thinking I might want to draw the one that we already drew, or the ones that we already drew. So I must have left my notes that I was working on in the science office. So I'm just getting this out. All right. So this was the handout that you were studying basically. This is all the stuff in Quizlet. And these are all kinds of plate boundaries all over the world that we're going to be working through and drawing diagrams for. And the two that we did last time were the Mid-Atlantic Ridge and the Andes Mountains. And I want to do those again kind of quickly, and just imagine that this is a test. So I'm not totally sure what your test is going to be like, but I think it's going to be a little something like this. So you'll have a plate boundary, and maybe I'll tell you the name of it, or maybe I'll just give you a map, and you're going to have to figure out what it looks like. So let's just say you have a map, and you've got two plates like this, and they're doing this kind of a thing. So what you would have to do on your test is give me the name of this plate boundary, write the name down, and then you'd have to draw a diagram of it, and then tell me all the kinds of things that you would find at this plate boundary based on this checklist. Some of these things we'll have here, some we won't. Like there's steep composite cone volcanoes. There's an ocean trench. There are relatively violent eruptions. So that's what we're about to do right now. And I think this will be good practice. So that's why I made these sheets with a little checklist on each one. So what you have to draw on every diagram are the plates and the mantle down below, and you have to shade everything and show all the features that are involved here. So what do I draw first? You should, Tommy, do you have something to draw with? Did I give you one of these? I should have given you this. Take that, take a sheet of paper. Here's what I'm going to do. I'm going to pose a question. Instead of asking somebody, I'm going to ask you to think about it, and then I'm going to give you the answer kind of quickly. In your mind, you need to see, do you know, could you do this yourself? If you want to try to stay a couple of steps ahead of me, go ahead. That's good practice. But if you want to follow along, don't get into the habit of just totally following along. You need one of these too? Yeah. Two-handed pencil throw. All right, so the first question is, how many plates do I draw and what color? Think about it. And the answer is 2. And the answer is they're dark because these are dark. So I'm going to draw 2 plates and I'm going to make them dark. Now I can go ahead and name this. These are both dark plates. That tells me the kind of plates they are. And then I can see the motions. So think to yourself, what kind of a plate boundary is this? Ooh, that's funny. And this is an ocean divergent plate boundary. And because it's 2 dark plates, so they're both made of felsic stuff. Felsic stuff means they're ocean plates, and they're divergent. So now in the diagram, I want to draw all the arrows showing how things are moving here. And I want to show the arrows down in the mantle. So think about how I would draw that. Ocean divergent. Divergent means they're moving apart. There's going to be something crucial going on right here. Think about what's happening there. So if these are moving apart, that tells me the current here is pushing them apart. And if these currents are coming apart, then what has to be happening is there has to be a rising current right there. And if this is rising up, something's got to be pulled in here to fill in for it. So we get these, this is the convection current down in the mantle. Now there's something else I need to do to the mantle. See if you can figure out what's wrong with my mantle before I fix it. Okay, here's what's wrong. The mantle is mafic. So the mantle is made out of the dense mafic stuff, and the ocean crust is made out of the dense mafic stuff. Anything less dense is going to be above ocean crust, or anything above the ocean crust is going to be less dense, except maybe in the case of the Hawaiian volcanoes, which we'll get to. I'm going to draw some water, just because I think oceans look better with water. So there's my ocean. Now I need to draw what's happening here where these 2 plates are meeting. So see if you can remember, or see if you can figure it out based on what you see here. And the answer is they get pushed up by this, but there's still a crack between them. So it sort of looks like a couple of canoes facing one another. And they get pushed apart, but there's also some stuff coming out of this crack right there. Now the next thing, do I draw a big volcano there from all this magma that's moving up, or do I just leave it like it is? The answer is I leave it like it is because this can never really pile up and make a big volcano because these plates keep splitting apart. So there is something else. There's one other kind of rock that I need to draw, and that is the seafloor sediment. And it's going to become sedimentary rock eventually, but it's thin in some places and thick in some places. Where would it be thin and where would it be thick? And the answer is it's thin on the new rock. This is where rock's being born right here. So the sediment is thin there, but it gets thicker as you move away. And this sediment, should I leave it light or should I make it dark? Is it mafic or is it felsic? I leave it light, yeah. So anything from the ocean crust down is going to be mafic. Anything above the ocean crust, like the sediment or the continental crust, which sits higher, that's all going to be felsic. And this is it. I'm not going to label this with words because I want to go through my checklist down here, and these will be my words that go with this. So first, this first one, there's steep composite cone volcanoes. A composite cone volcano looks like this. You've got a dark layer and a light layer and a dark layer and a light layer. If you cut through a composite cone volcano, you would find a bunch of different alternating mafic and felsic layers. So do we have one of those here? Anybody see a steep composite cone volcano? No. So we don't need to check that one. If you want to X them out, you can. An ocean trench here. Kind of looks like maybe a trench, but let me, just to clarify, this is what causes a trench. When one plate dies beneath another one, like this, right there, that's where you get an ocean trench. This is more a ridge than anything, where these two sides there really wouldn't be any space between them because this would be filled up with new rock that's swarming. So there's no trench. Relatively violent eruptions of lava. So the way we figure that out is by looking at the type of lava. Is this lava mafic or felsic? I'll draw a little diagram up here. This is mafic. This is felsic. Which kind of lava do we have going to the surface? Do we have lava? Right here. That's where the lava comes up. Is that lava coming from a source that's light or dark? And the answer is it's coming from down here. So that's mafic. So no, this is not going to be violent because this is the runny kind of stuff. So no. But number 4, relatively gentle eruptions of lava, yes. I'll put a mark in that box, or you can just darken that box. Now this one about shallow earthquakes in the crust can happen here. This is always going to be true. Every single thing we do, you can always check that box because as this magma comes up or as it pushes the plates apart, sometimes the plates don't just move smoothly apart. Sometimes they get kind of stuck and suddenly move, and that causes an earthquake. So anywhere where plates move, you can have shallow earthquakes. Some places, there are earthquakes that happen down deep, but not here. There's only when this happens. Only at things called subduction zones do you have those. So no deep earthquakes. This is a subduction zone. Subduction zone is when one plate goes beneath the other, so no. All right, here's a good one. You all know the answer to this. The mantle beneath this area is relatively cool. Look at that mantle. Think to yourself, is that true or is that false? That would be false, because this is rising, which means it's relatively hot. New ocean crust is being created here. Is new ocean crust being created? Yeah. So this, where I'm putting this little dot right here, that used to be here. And before it was here, it was over here. And the first place it was right there. All this stuff, this mafic stuff is coming up and hardening on the sides of this crack, and it's making new ocean crust. This is mafic. The crust is mafic. It's the same stuff. It's only this is hot and flowing. This has cooled and solidified. So yes. Now we get mantle below this area is relatively hot. Is this hot? Well, it's rising. So yes, rising stuff is relatively hot. This next one, tall mountains but no volcanoes. I don't know. I could see this. The name for this is called the Mid-Atlantic Ridge. So if somebody checked that, and they said, Mr. Stapleton, I want credit for this because this is a ridge, so there are kind of tall mountains here. I'd probably give them points, but I'm not going to check that. I'm not going to call this the Mid-Ocean Ridge Mountains. Maybe I'm wrong. Somebody's going to watch my video maybe and complain, but in my diagram, it doesn't really look like they're mountains, so let's say no mountains. So no. And finally, there are rounded shield volcanoes. There aren't any real volcanoes. Now, an exception to this is Iceland. Iceland is on the Mid-Atlantic Ridge, and some other stuff is happening, but we're not pretending this is Iceland. So there you go. If this had been the test, that diagram would have been great. And the only 4 things that you would have checked would have been those 4. So instead of, I kind of was thinking maybe we should do the other one we already did, but let's not. Let's move on to a new one, a different one. And the one I want to go to is this, the Himalayas. And if we want a particular name for this, what's the famous mountain in the Himalayas? The really big one. I'll give you one of these. Solely, you need one of these too. You got one? That's okay. Oh, that's what he gets for showing up late. Okay. So does anybody know the big mountain in the Himalayas? Mount Everest. So Mount Everest is somewhere right around here. This is India, and this is Asia, and they're really connected now, but a long time ago, India was down here, and it moved, and then it slammed into Asia. So right now, it's really 2 pieces of continent, India and Asia, that are crashing into one another. So the name of this kind of boundary, since it's continent, and they're moving into one another, it's continent-continent convergent. The important part about what we're doing to me is all the concepts that help you understand what's happening here. That's the kind of thing that when you get to chemistry and you get to physics and you get later in life, that's the thing that'll stick with you probably, not the details about what's happening here, like being able to check these boxes. But making sense of all this, that's the important thing. Being able to think about density and viscosity and those kinds of things. All right, so ask yourself, how many plates do I draw? What color should they be? Which way should they be moving? Just based on this, you should be able to get all that. I'll give you a second. You can try your own. So we're going to do the plates and then the mantle down below and show what happens to them. So I think I mentioned this to you last class. Continental crust is a little bit thicker. So I'm going to draw these a little bit thicker than maybe I did up there. But they're both continents, so it's not like one needs to be thick and one needs to be thin. So here are my 2 plates. And they're convergent. And that means that the current down below is moving the same way as the plates. And the thing that would cause the current to come together right here, or if these 2 currents come together, what they're going to do is they're going to go down. So if I want to continue the currents, sometimes I draw the currents first and sometimes I add it in later. Just thinking about, because I have to erase some stuff. If I have subduction, one plate goes over the other one. And one other thing I want to do is make this dark. Because the mantle is mafic and continental crust is felsic. Now, 2 plates are hitting one another, like this. When we did this before, we had, I wish I had a black, oh, you know what? I've got a black glove. This will be fun. Hold on. This summer I was working on making face shields, and I was supposed to wear black gloves. So now if this were a continent and ocean crust hitting one another, the ocean crust would be more dense, so it would go down like this, and the continent would stay on top. But if we have 2 continental plates hitting, what happens then? Like this? So that's a good idea, except if we do this, what about all this space here? It looks like a tent with a big space. Do you think miles of, so if this is Mount Everest, is there a hollow space below Mount Everest? And so it's like Tommy said, neither one, this plate and this plate, they're not dense enough to go down into here. This is like a piece of foam floating in water, and you can't get the foam to dive. So they're going to smash into one another, and neither one of them is going to dive, but it's going to be like a cheese log. And this is where I have to introduce all my students to cheese logs. Cheese log. To be honest with you, I've never done this with a cheese log, but I can imagine doing this with a cheese log. Cheese logs they're just soft cheese, usually with a bunch of nuts stuck in the outside. So these are logs of soft cheese that can be spread. Now, if I had a couple of those cheese logs and I squished them together like this, they would kind of go and basically smush like that. That's the way I imagine the cheese logs looking if I smashed them into one another. And this is really what happens. And this, if we're talking about India and Asia, this would be Mount Everest. And the example would be the Himalayas. And this over here, this, I guess it depends on the direction we're looking from, but if we're looking at this from the east, then this would be India, and this would be Asia. And Mount Everest is right in between. So as these squish together, this gets taller and taller, and this actually goes down too. So you can think of a root of the mountains going down into the mantle a little bit, but it's not as deep as if we had subduction like this up here. It's not like that. And that's it. There's really nothing else that's going on here. I do want to, I'm going to make some little stars because we haven't done this one yet. These are all places where earthquakes could occur. At all those little stars right there. Okay, so ready to answer the questions. Are there steep composite cone volcanoes here? you see any volcanoes here? For volcanoes, there have to be lava, and there's no magma, no melted stuff. All the stuff in the mantle is not getting up there. So there's none of that. How about an ocean trench here? Nope, there's no ocean, so we can't have one of those. And this relatively violent eruptions of lava, gentle eruptions of lava, are there any eruptions of lava? No. If you go to Mount Everest, you don't have to worry about lava. It's not an issue. Shallow earthquakes in the crust can happen here. What do you think? Remember what I told you? Always, 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 always. That could happen if there were no Mount Everest at all. If it were just this plate, in the middle of a plate, the plate can suddenly move faster, and then you get an earthquake. But right here, where this whole thing is kind of cracking and can have earthquakes all along here. And unless you have a plate diving like this is where you have deep earthquakes. So we don't have a plate diving. We do have the bottom of it kind of going a little deeper than normal, but it's not really diving. So there are no deep earthquakes. It's not a subduction zone. Again, a subduction zone is when one plate goes beneath the other. That's what a subduction zone is. This one we can do. Is the mantle beneath here, is this relatively cool? Yes, and the way we know is because the current is sinking here. So if it's a sinking current, then the mantle is relatively cool. How about new ocean crust? Does anybody see any mafic lava hardening to become ocean crust? Shouldn't be any. Mantle is relatively hot? No, because it's cool. How about number 11? There are tall mountains here, but no volcanoes. Does that apply? Yes. So this is the one. This is the only one, really, where you will be checking this. There's no volcano. This is not a volcano, but there are tall mountains because they're just smashing into one another and pushing this up higher and higher. Mount Everest is still growing for that reason. And then finally, rounded shield volcanoes, no, there are no volcanoes. So the only things that we have here will always have shallow earthquakes. The mantle below is cool, and then there are tall mountains, but no volcanoes. And we've got some more to do, but I don't want to do any more drawings today. I want to show you, maybe show you a few pictures, and then we'll be done. So let me go back to see if I can find my way to my website. I've got all these cheese logs. If you'd like to look at the Google Slides that I have, there's some good, or at least pretty good pictures of things. All right, so this is not a great picture of the Mid-Atlantic Ridge, but it's about the best thing I have. So you can see Africa, and then South America, and right down the center is the Mid-Atlantic Ridge. It's a bad picture. Let's see if I can find better ones. This is pretty good. I like this one because it's not too spectacular. It's just this crack running right down the center of the Atlantic Ocean. And when people show pictures of the Mid-Atlantic Ridge, they usually show the exception to the rule, and the exception is Iceland. Here's the Mid-Atlantic Ridge. Here's another one of the Mid-Atlantic Ridge. But way up at the top, I'll open this one up a little bit bigger. Way up at the top here, Iceland is actually on the Mid-Atlantic Ridge. And I think the reason that Iceland was able to build up is that in the particular place where Iceland is, this splitting must not be happening very fast. So this magma that's coming up can actually pile up in Iceland. And I would guess that if you went farther north from Iceland, these plates would stop splitting apart. It's sort of on the end. It's like if I made a rip in this paper, like this, and I start to rip my paper apart. And right in the middle, I've got this big tear that's opening up. But right here on the ends, right there, that's kind of where Iceland is. So if there's magma coming up, it can't really fill in this space right here, but it can start piling up there. So that's the Mid-Atlantic Ridge. And let me show some more of these. Oh, that's not even my slideshow. Where is, okay. So this is a picture of the Indian plate, and then the Eurasian plate, and then you can see the Himalayas right in there with Mount Everest. So that's what we were just drawing. And they look like this. You know, they're sharp and jagged, and there are a lot of glaciers on top of those that are carving them, but they're not volcanoes. There's not the symmetry that you see if you look at something like this. This is much more typical of a volcano. This is a composite cone volcano. Or this is Mount Fuji, supposedly the most photographed mountain in the world. People really love to take pictures of Mount Fuji in Japan. So those are volcanoes, but these are not volcanoes. All right, people at home, all you have to do is just make sure you know that mafic and felsic stuff. You're going to have a quiz on Thursday, and you're good to go. Thanks for coming.